Hello students, welcome back. How have you been? All good? Okay, so I'm your teacher Arpita Sharma and we are going to start the very second lecture of this chapter, area of parallelograms and triangle. Okay, we have talked about area of parallelogram and triangle. Okay, and I have talked about the same base and the parallels and the triangles and parallelogram between them. Okay, so there are some important things that you have to know. First thing that you should know the formula for the area of a parallelogram first. Second, you have to know the area of a triangle. Second, both you know. Okay, now one more point we have to discuss, and the point is that area of congruent figures. Area of congruent figures are equal. Area of congruent figures are equal. That means if I'm having two let's suppose triangles, okay, and they are congruent, so then the area of these two triangles will also be equal. But if the area of two figures are same, that doesn't mean that they always need to have the same congruent figures. That means if I'm having a triangle here, this triangle ABC, which is congruent to this triangle PQR, okay, then I'll be writing this, that area ABC is equals to area PQR. And why that's why, because we are having triangle ABC congruent to triangle PQR. And let's suppose the area is some 21 units square or square units. This is the area of this triangle. So that means the area will be here also 21 square unit. But let's suppose I am having a circle. Now I am having a circle and the area of the circle is also 21 square units. It can be, right? It can be possible, okay, that area of this any circle can be of 21 square units. Now I am having this 21 square unit and this 21 square unit. Even the areas of these two figures are same, but they are not congruent to each other. They are congruent, then definitely they are going to have the same area, but the converse is not true. So clear with that portion? Okay, this was the very first thing. And what is the second other thing? I have told you I will be talking about two things, okay? So the first thing was this. Now second thing about the area also, we have to understand if we are having a complicated figure, like I'm having this figure, okay, so basically this is made up of this area P. Let's suppose this is area P and this is area Q, and let's suppose the complete area, the total area is area T. Then this area T will be nothing but the area of two non-overlapping. That means if this is the area P and this is the area Q, these both must not have any common areas, okay? In that condition only, the area T will be equals to area P plus area Q. And if they are like divided in some not overlapping areas like P, Q, R and S, then the summation of all these areas will be leading to the area of the total place, that means total region, that is area T. So you understood this? Now we are clear about this part, okay? Now in the previous lecture I have left you with this theorem, not question, but theorem, that parallelogram on the same base and between the same parallels are equal in areas. And we'll be having this kind of parallelogram here, that we can understand that there we are having this okay, so basically we are having this parallelogram D, C, F, E, okay, and then we are having another parallelogram which is A, B, C and D. We are having two parallelograms here, okay, so they are on the same base and between the same parallels. So we have to prove that they are going to have the same area. Now, is that possible? Okay, so we'll talk about it. So what we are having, what is to be proven is like they are parallelograms. So we can say that we are having this given thing that AF is parallel to DC. Similarly, we are having this AD parallel to BC, AD parallel to BC. And similarly, if these two parallels, we are having these two parallels also, these two pairs as parallel lines also, because this is also a parallelogram. So ED is parallel to FC. Now what we have to prove that these areas, okay, these areas of these two, green rectangle and the pink, sorry, not rectangle, but green parallelogram and the pink parallelogram, both are the same because they are having the same base. Okay, let's suppose, let's see if it's true or not. Okay, so we are having these two triangles here, the first and second that you can see. Okay, what we have to prove is area A, B, C, D is equals to area A, B, C, D is equals to E, F, okay, C, D, E, F, okay, C, D, E, F. We have to prove that. Fair enough. Now, I'm going to take this triangle and this triangle and I'm going to prove these two triangles congruent. If these two triangles are congruent, I've just told you that then these two triangles will be having the same area. Okay. So, talking about the proof, here we are having in triangle AED and triangle BFC, we are having this angle A is equals to this angle B, okay, this EAD is equals to this FBC. First thing, why? And also these two triangles I have told, angles I have told you these are equal, and if you look closely to these two angles, these angles are also equal. I'll tell you why. So this angle, this angle is AED, and which is equal to angle this BFC. Why? Because they are corresponding angles. Cause this line AD is parallel to this line BC. So if these two lines are parallel to each other, these will be the corresponding angle which are again equal. Okay, if these two lines ED and FC, the green ones, the ED and the FC are parallel to each other, in that case these two angles will be again the congruent, the corresponding angles. So these two angles, okay. Now AD is parallel to BC. If AD is parallel to BC, that does mean that these two sides are equal. So I can write it also here that AD is equals to, also AD is equals to BC. Why? Because A, B, C, D is parallelogram. So now I can apply what? By two angles and a side, congruency, triangle AED is congruent to triangle BFC. These two triangles are congruent to each other. I have proved that. Okay, so we have proved that these two triangles are congruent. If these two congruent triangles, then we must say that the area of AED is equals to area of BFC. Why so? Okay, I've just told you that congruent figures must have equal areas. We have talked about it. We have talked about this. So, here you'll be having this area AED is equals to area BFC. This complete area is equals to nothing but this complete area. Now, look at it here again. We have to prove that area ABCD is equals to area CDEF. Now, this particular thing that we have find out, I am going to put it here. Okay, so we have find out that area AED is equals to area BFC. Fair enough? Okay. Now I'm going to rub this part. Noted now? Okay. Now we'll pick one of the parallelogram and we'll prove it to the another one. Okay, so which one you are going to pick? Okay, let's suppose we are picking this ABCD. Okay, so or you can say this the second one C D E F. Okay, area CDEF. Okay, this area CDEF is equals to what? This area CDEF is equals to what? I can say that if I'll take this complete portion and I'll add it to this complete portion, then that will be making this EFCD. Okay, no doubts. Okay, so I'm going to write this area EBCD, this particular area, plus area this what? BFC. So area BFC. Understood? Okay. Now I'm just going to replace this area BFC as the area AED. Okay. That is equals to area EBCD plus area, in place of BFC I'm going to write AED from equation 1. I'm going to put the value here. Now look at it here, that will be equals to that will be equals to what? EBCD. Now EBCD is this, not green color, I have to take another color. Okay, yellow. EBCD, this area plus AED. AED is this area. So totally it is making this area, and this area is what? ABCD. So it is now, and this is now equals to area CDEF is equals to area AB, C, D. Hence, proved. Understood this thing now? Okay, clearly? Okay. Let's move to the next question. Now, in this figure, ABCD is a parallelogram and EFCD is a rectangle. Also, AD is perpendicular to DC. Okay. AL is perpendicular to DC. Here we are having AD is perpendicular to DC. What is AD? This is AL, sorry. AL is perpendicular to this DC. Okay, this is given. Now we have to prove that area ABCD is equals to area EFCD. Area ABCD. Area ABCD is this area. And this need to be equal to the area EFCD. EFCD. This area. Okay. Okay. Now EFCD is a rectangle. EFCD is a rectangle. Okay. Fine. This is gonna be so easy. Okay. How? Okay. We'll go with the proof part only. Okay. We are jumping the first one. The proof part. You'll write the given things. Okay. So, DC is common base. Okay. And EFCD is a rectangle which is also a parallelogram. It is given that it is a rectangle. Okay, it is given this is a rectangle. Right, students? If it's a rectangle, then this is also a parallelogram. Because if I draw a parallelogram and if I put the condition that the angle of these parallelogram are what? 90 degree, then that will be becoming a rectangle itself. Okay, and then I will be putting on a condition in that all the sides will be equal, then that is going to be a square. So this is the case of rectangle. So basically rectangle is also a parallelogram. Okay, so theories of parallelogram are going to be fit in here. Right. Okay. So first DC is a common base and EFCD is a rectangle. Okay. EFCD is a rectangle which is also a parallelogram. Now, by theorem, in this lecture, the very first theorem we have proved that parallelograms within the same base and between same parallels are equal in areas. Parallelograms having the same base and between the same parallels are equal in areas. This implies that simply this area ABCD is equals to your EFCD, this EFCD, area EFCD. Okay, so the first part is very simple to prove, right? Okay, so we have proven this first part, right? So first part we have proved. Now for the second one. Area ABCD equals to DC multiplied by AL. Area ABCD. Area ABCD this area is equals to what? This AL multiplied by CD. Okay. So we are having these two, AL and DC things involved here. So what are we and what we are now going to do? Okay. Proof. ABCD is a rectangle. Okay, this is given. So area ABCD is equals to base into height. Oh, sorry, not base into height. This will be the side ED multiplied by side, the second DC. Okay, or you can just write side ED multiplied by DC. Okay, now this line we are having here, AL perpendicular to DC and also ED is perpendicular to DC. Okay, this ED perpendicular to DC and this AL also perpendicular to DC. That means this ED will be equals to AL because they are between the same parallels and this is also the perpendicular, this is also the perpendicular. So perpendicular distance between two parallels will always be the same, right? So okay, this implies that AL equals to DC. This is the second equation, this is the first equation. Okay, put the value from second in 1. Okay, that means area ABCD is equals to what? ED. ED we have replaced it with AL. So AL multiply by the same DC. Okay. So AL multiply by, sorry, this AL multiply by this DC. Okay. Now this we are having the area of ABCD, but we have proved that area of ABCD is equals to area of EFCD. Okay. Here we have to prove only about the area of ABCD and we have proved this DC multiplied by AL. So this is area of ABCD is equals to AL multiplied by DC. Hence proved. Okay. So done with that question. Okay. Now the next. Now we are having if a triangle and a parallelogram on the same base and between the same parallels, then prove the area of a triangle is equals to the half of the area of the parallelogram. Okay, in this question we have asked that if I have drawn two parallels, okay, and we are having some base AB, so I'll be having a parallelogram ABCD here. Now having the same base BC or equals, sorry, AB, and having the same base AB or having the base equals to AB and having the same parallels, if I draw any triangle, the area of this triangle will be just half of the area of the parallelogram with the same base or equal base. Okay. This we have to prove. So we are having this ABCD parallelogram here. Okay, and we are having this triangle PAB here. We have to prove that area PAB is equals to half of area ABCD. Okay, so we can write that to prove what we have to prove, that area PAB is equals to half area ABCD. And for this, we are having a construction, a small construction. And the construction is that we draw this BQ parallel to this PA, so that we'll be having this new ABQP is parallelogram. Done? Okay, so this is the construction part. We have constructed this. So we have made this a parallelogram. Okay, so now I'm having this parallelogram and I'm having this triangle, and I will prove that the area of this parallelogram is double the area of this triangle. Okay, if I'll prove that, then I can apply this theorem. The area of two parallelograms between the same base and having the same base and between the same parallels are same. Okay, so we are going to use these two theorems. Okay, one theorem and one trick here. Proof. In parallelogram ABQP, triangle APB and triangle APB have taken, so will be taking QPB. Okay, QPB. Look, we are having PB is equals to PB, PB equals to PB. This is common side. First thing, okay. Then this PA is parallel to this QB, so PA is parallel to QB. And PQ, PA, BQ is parallelogram, right? And also by this we can say that these two lines PA and QB, PA and QB are equal. This PA and QB are equal. Now here this PQ and AB, PQ and AB are also equal. And why these two are also equal? Because they are also the opposite sides of parallelogram. So you can just write it here that these are the opposite sides of parallelogram, and name the parallelogram APQ, ABQP, right? Okay, so we can say that by SSS congruency, we'll be having this area, not area but triangle APB is congruent to triangle QPB. If these two are having the congruency among them, between them, then we can say that simply area of APB is equals to area of QPB. That means these two triangles are sharing the same area, are having the same area, right? Okay. Have it as the first equation. Okay, so we have this as the first equation. I'm clearing up the board. Not clearing, let's wait. Okay, so I'm clearing the remaining part. Okay, only the result part we are keeping. The first equation that we have arrived, we have derived. Now This part is here again true. Now this ABQP, this area ABQP is equals to area APB plus area QPB. Okay, this area APB plus area QPB. These two triangles are making this complete parallelogram. So we can write it, but these two areas are equal here by 1. Putting values from 1, we can have that this area ABQP is equals to, this is APBB and this QPB is also is equals to area APB. Okay, so we can substitute it here, area APB, or we can say PAB. Okay, and this is also PAB because these two are equal. Okay, we can say that by this we can say that area AB QP is equals to area PAB, right? Okay. So we have derived that area ABQP is equals to 2 area PAB. Now we are having this AB parallel to this PC, right? And we are having this base AB for this parallelogram ABQP. Have a look here again. ABQP, and also this is the same base for the area ABCD. So again we'll be having the same base, and between the same parallels the parallelogram will be of the equal area. Okay, so we are going to use that. Parallelogram ABQP and parallelogram ABCD are in same parallels and between and on the same base. This implies that area ABCD is equals to area ABQP. Make it equation. That was our first equation. Put it second and put it third. Okay. So after that, we are just going to say that putting values from third in second, we are gonna have that area ABCD is equals to 2 area PAB, and that will lead to area PAB is equals to half area ABCD. Okay, this was something we have to prove. So hence prove. Right, now have a look of this again. I'm not completely doing the question, but I'm just making you understand the technique. We have asked that we are having a base AB and we are having a triangle ABQ and a parallelogram ABCD on that. We have to prove that if we are having two parallels, Okay, and we are having a common base, then in that particular case, the area of this parallelogram will be just double of the area of triangle, or maybe that maybe we can say that this area of the triangle will be the half of the area of parallelogram. For that, what we'll do, we'll just construct a line parallel to this PA, and we'll name that like BQ. Okay, and that will take this parallelogram and will prove that these two triangles are congruent. So the area is also congruent. If the area is congruent, then basically the area of one triangle is just half of this particular parallelogram. But the parallelogram's area is also same because they are having the same base too. So by that we just prove that indirectly. Okay, so this was about this question. Okay. Now have a look in the next question. This is the exercise question. The figure you are given with the ABCD parallelogram, and A is perpendicular to DC. Okay, so A is perpendicular to DC and CF is perpendicular to AD. If AB is given, okay, so we have given with some digits and units here. So AB, okay, AB is equals to 16 centimeter. This is going to be a very quick solution. And A is equals to 8 centimeter. Okay. And we are going to have the CF. CF is equals to 10 centimeters. Okay. Then we have to find the AD. The AD. We have to find out what will be the value of AD equals to what, right? Okay, so in that case we are going to know about this AD. Now this is a parallelogram, right? Okay, if this is a parallelogram, what will be the area of this parallelogram? The base multiplied by the altitude. Okay, area of parallelogram what is our parallelogram? ABCD. Okay, so ABCD is equals to base multiplied by altitude. Now, if we'll take DC as base, then the altitude will be AE. Okay, also area ABCD is equals to, if I am going to take this AD as the base, then the altitude will be FC multiplied by FC. This is the first equation, this is the second equation. By equating 1 and 2, I've got this DC multiplied by AE is equals to AD multiplied by FC. Got it? If that's so, in that case, what I'll be having, I have to find out the AD, value of AD we have to find out. Okay. What and what values we are having, just find out that also. So first come first, we are going to have to find the value of AD. So for sure we are not having the value of AD. Okay. Then we are going to have the the value of DC. Now the value of DC is this DC. Now AB is parallel to DC here. Okay, so opposite sides of parallelogram. So these will be equal. So equation third is this. Right. DC will be equals to AB. Y equals to B is given 16 centimeter. And this is Y. Opposite sides of parallelogram. Okay, opposite sides of parallelogram, so AB equals to 16. AB now will be having DC. Okay, so we will be having DC. AE. AE is given 8 centimeter. Okay. Then we'll be having FC. FC is given 10 centimeter. These two values are given. Now, put values in equation 3 or third. What will be having? DC which is 16 centimeter multiply AE which is 8 centimeter is equals to AD, that we have to find out, multiply by FC which is given 10 centimeter. Okay. Now, this will imply that AD will be equals to 16 multiplied by 8 divided by 10. Okay. From here, you'll be having 128 by 10. This will be going to be. Now, with the units, we'll be going to have this centimeter. And what is this? A side, not an area. That will be our answer. Okay, so that will be your answer for sure. Now, understood that thing? Okay. Now, we are having this next question that will be seeing in our next lecture. And the question is, if E, F, G and H are respectively the midpoints of the sides of a parallelogram ABCD, show that area EFGH equals to half area. This is nothing here. Area ABCD. Okay. Right. It's saying that we are having this ABCD. We are having midpoints as E, F, G, H. Okay. If we'll meet these 4 points, here we'll be also having a parallelogram or a quadrilateral, you may say like that. Okay. Now you have to show that the EFGH, the area of this EFGH will be equals to what? Half of the complete area. Complete area is half. What we will do, I'm just telling you the construction part here. You will be drawing a line HF, and HF will be going to be parallel to this this DC and this AB. Why? Because we are having the midpoint of AD and we are having the midpoint of BC. Now, if you are going to take midpoint of two opposite sides of a parallelogram, then you are going to end up with a line which is perpendicular or which is parallel to both the lines. Okay. So, with this note, I am going to end this lecture. We are going to meet again in next lecture. We finding the solution of this theorem. Right? Okay. Take care of the student. Bye-bye.